This paper is about a large deformation analysis developed to simulate penetration resistance of offshore pipelines. This is the outline of the paper. First, I will give you an introduction about offshore pipelines. Then, the large deformation finite element analysis developed for this analysis, numerical model, mesh sensitivity, vertical penetration resistance of pipelines, then the soil flow and pore pressure distribution around pipelines, including the failure mechanism, lateral penetration resistance, and finally the conclusions. So, in deep water, offshore pipelines are laid over seabed directly without any additional restraining mechanisms or trenching. Forces due to wave action and pipe-laying equipment contribute to the initial positioning. Geotechnical design of pipelines is underdeveloped compared to other foundation types. Pipeline design is different to other foundation types because the lateral deformations of pipelines are very large compared to other foundation types such as piles and shallow foundations. Because in piles and shallow foundations, lateral deformations are normally a fraction of the foundation diameter, but in the case of pipelines, the lateral deformation can be more than 10 times the pipeline diameter. Because of that, pipeline design is not similar to the uh, pile or shallow foundation design. So, classical plasticity theory has been widely used to investigate the failure mechanisms and ultimate loads during pipe penetration into the seabed. Centrifuge test data developed are widely used to validate numerical models and uh, analytical solutions. Normally, small strain based finite element modeling is not suitable to simulate the pipeline penetration because of the large soil deformations around pipelines during seabed penetration. Uh, in the small strain analysis case, normally the penetration is simulated from a wished in place condition. That means it is embedded at one point in a certain depth and penetration is continued from that depth. It is not from the ground seabed surface to the uh, deeper depths. Recently published research considering large deformation finite element analysis uh, considered the strain softening of soil and the rate effects, but the pore pressure effects are not captured. Because of that, in this paper, coupled large deformation finite element analysis has been proposed incorporating the pore pressure effects to simulate the pipeline penetration and subsequent lateral deformations in the soft. The analysis procedure developed in this paper is written using the Python development environment, which is called PDE, within the Abacus Standard Finite Element Program. Analysis is carried out in a series of small strain finite element analysis stages. Abacus input file for each analysis was created using the Python code developed by me. After each analysis, the deformed boundary is captured and a new mesh is generated. All variables corresponding to integration points and nodes of the old mesh were transferred to the new mesh using the solution mapping algorithm in the abacus. During solution mapping, all variables corresponding to integration points of the old mesh are transferred to nodes of the old mesh and averaged when a node is shared by several elements. Then the interpolation is carried out to the integration points of the new mesh. Variables transferred from the old mesh to the new mesh are initial conditions for the new mesh. The duration of each analysis should be determined by taking into account the mesh deformations because accuracy of this analysis depends on the mesh deformations at the end of each remeshing step. Therefore, the criteria for the generation of the new mesh using the boundary of the deformed old mesh should be set before excessive mesh deformations. If there is a discontinuity in the solutions, it can be due to the use of two coarse mesh or carrying out remeshing when the elements are excessively distorted. Specific details using this approach is presented in the paper, and you can refer to the paper for more details. This is the numerical model. The pipeline penetration is started from the ground surface. Pipeline is modeled using CPE4, that means plane strain 4 node elements, and soil was modeled using the same element with pore pressure degrees of freedom at the corner nodes. We have not used nonlinear elements because convergence is a problem when we use CPE8R and CPE8RP elements. Wang and others presented a large deformation analysis considering undrained behavior for seabed soil without considering pore pressure effects. Then again, we have found some centrifuge modeling data. Again, penetration rate is high to simulate undrained conditions. This paper is published by Ding and others in 2008. So, in our paper also, we used a coupled analysis, but uh, consolidation analysis simulated using a fast penetration rate of 1 millimeters per second to simulate an undrained condition, because then only we can compare it with the published results from previous cases. So the material properties for the seabed are given in the paper, and also for the pipeline. Very high stiffness is used for the pipeline to avoid any deformations, and also pipeline is modeled using elastic material properties. So the mesh sensitivity study carried out shows that when we use a zero point 0.2 meter element node spacing, there are some distinct discontinuities in the penetration resistance. This is a vertical penetration resistance. But if we model both pipe and soil using zero point 0.1 meter node spacing, we can get a smooth penetration resistance. Because of that, we use this fine mesh for the following analysis. So the vertical penetration resistance from the centrifuge model using a smooth surface from the finite element analysis and surface friction of zero point 0.5 and limiting the shear stress at the interface to 2.5 kPa, and again without shear limit are presented in this paper, this figure. And you can see that when the interface is smooth, penetration resistance is the least, and it matches well with the purple line where the interface friction is zero point 0.5 and there is no shear limit. Red line is also close enough for the centrifuge results. In this case, we compared with large deformation analysis results from Wang and others and upper bound solution proposed by Randolph and White in 2008. You can see that the current analysis is given by this broken lines for the smooth surface, alpha zero point 0.5 and limiting shear using this firm black line, and the upper bound solution with rate effects and softening, this light blue line, and Wang's results are the other lines. We can see that the current analysis is a good match with other cases presented by, see this blue line, sorry, green line, alpha zero point 0.5 by Wang and White, and purple line is with full friction. This is the soil flow around the pipeline. Actually, these flow patterns match very well with uh, centrifuge model results. This is the pore pressure distribution. Then the failure mechanism. Again, it shows a fan faced area and a linear line moving to the surface of the soil. This is the lateral penetration at different penetration levels, pore pressures, and the penetration resistance, horizontal and vertical, because during the lateral penetration vertical penetration resistance decreases, but the lateral penetration resistance continuously increases. And this is the failure mechanism evolving around the pipeline during lateral penetration. This fan faced area is can be simulated using a circle. So these are the conclusions. So this is a new analysis method using the Python development environment in Abacus. It has the ability to simulate deep penetration problems, and results confirm that the proposed coupled analysis approach is useful tool in simulating deep penetration problems in geotechnical engineering.